This is a good problem to start with for implicit differentiation, because you can kind of see it's not just a very simple, y equals something. I have this y squared there, so it's going to make it a little bit more complicated. The question says find dy over dx. Just let's remember what this means. This is saying the dy means if I have a little bit of change in y, just a little tiny bit, I have a little tiny bit of change in x. So it's asking me a little bitty tiny change in x is going to cause what kind of a change in y. In other words, if I have an xy axis and I had a function and I want to know this little bitty change in x is going to cause a little bitty change in y. But I want it to be so tiny that it's just at that one point. Do you remember? F of x plus h minus f of x all over h, the limit as h approaches 0. So when you see this notation, dy dx, all it's saying is find the derivative. It's saying find me the rate of change at an exact point on this function. The change in y divided by the change in x at one point on this function. So let's get back to the problem. I need to find the derivative, dy to dx. What is the change in y with respect to x? Excuse me. So I'm going to take a derivative of each side of this equation. So it's just like doing any kind of operation on an equation. If you do it to one side, you got to do it to the other side. So I'm going to take the derivative of this. I'm going to go the derivative with respect to x of that. And I want the derivative with respect to x of that. Now, the right-hand side over here is going to be pretty straightforward. The left-hand side is where implicit differentiation is going to come into play. So let's do the left-hand side first. This is going to, I'm going to follow the power rule, and it's going to be 2y to the first. But you got to remember, if you think about the chain rule, y itself is a function. So I have to multiply this by dy over dx. I don't know what that derivative is yet, but I know that when I'm taking the derivative of a function, I'm going to end up taking the derivative of the outside, which is the function y, and then I'm going to work my way to the inside until I get to the derivative of x. So I'm going to have 2y times dy dx, and that equals, well, on this side over here, I'm going to be using the quotient rule, which is u prime v minus u v prime over v squared. I'm just finding the derivative like I would normally. So if I go, the derivative of my numerator u is simply 1, and I'm going to multiply that times v times x plus 1. And I'm going to subtract, well, the derivative of my, I'll take my numerator, which is x minus 1, I'll put this in a bracket here, times the derivative of my denominator, which again is just 1. And I'm going to divide that by x plus 1 squared, just using the quotient rule. Okay? So now I have 2y times dy over dx is equal to x plus 1 minus x plus 1, just distributing my negative sign, over x plus 1 squared. So that equals, well, that x and that x are going to cancel out. So I have 1 plus 1, 2 divided by x plus 1 squared. And that is 2y times derivative of y over derivative of x. And all I need to do now is divide both sides by 2y. I think what I'll do is I'll multiply by 1 over 2y. Has the same impact. So those cancel out. The 2 cancels out. So I have my derivative of y with respect to x is equal to, well, it looks like 1 divided by y, x plus 1 squared. And that's the answer. Just remember, when I take a derivative of y, so I want to find a derivative of y with respect to x. Let's use y squared as our example here. I'm going to take the derivative. I'm going to use the power rule on y. So that'd be 2y. But I have to multiply, since y is itself a function, I have to multiply it by dy over dx. That's the mechanics of this thing. It's telling me that y is a function. So I know that my derivative here is going to be 2y, but it also has to multiply by the inside function, which I can't really see, but that I know is the derivative of that inside function, dy dx.